Today we're looking at a topic called compounded interest, and this is, I would say, a really important topic, especially when you're dealing with different loans that you'll be experiencing throughout your life. Terms that we need to be aware of, something called compounded interest, what it is that we're actually doing. That is just the interest that is added on to the principal. So remember, a principal could be an investment, could be the amount of your loan. That's what you're beginning with, that's your beginning rate. Compounding frequency. That is the number of times per year, or at times, not very often, but sometimes it's a different unit of time. That is accumulated the interest in paid out or credited to the account. So number of times of year that we are going to say we're going to take that principal, we're going to start to earn some interest, and then we're going to put it onto that account. Okay. So we're going to try a problem. So we have a person invests $500, that's your principal, into an account that earns a nominal yearly interest rate of 4%. How much would this investment be worth in 10 years if the compounding frequency was once per year? Okay, so we're just doing a one time a year frequency compounding. So just once at the end of the year, you're going to get your interest rate applied. So this should look something very similar to things that we've done in the past, where we have our principal and our interest rate is 4%. So we want to think 1 plus the interest rate expressed as a decimal. And then we're going to raise it to the number of times it would be compounded. I'm sorry, the number of years it's going to be compounded, which is 10 years. And if we were to simplify this, plug this into the calculator, get out a final answer, we're going to find around $740.12. So only compounding it once at the end of the year, but for a total of 10 years. After that 10-year period, 4% interest rate, that $500 now is a total of $740.12 into your account. If, on the other hand, the interest is applied 4 times per year, known as quarterly compounding, why would it not make sense to multiply by 1.04 each quarter? All right, so we have to think about this. This 1.04, that's telling you 4% per year. Okay. If this was per quarter, it would have to be way more. Okay, so this would be saying that we would be getting so much more added on, way different. This is only per year. This one's saying, but we wanted to do it compounded quarterly, we should have something way bigger than that. All right, so what would happen? So if we were told that an investment earned 4% per year, how much would you assume it was earning per quarter? Okay, so if you have 4% per year, but it's going to be calculated per quarter, that means 4 times a year. I'm going to divide that by 4, and that would tell me 1% per quarter. Okay. So it says using our answer for part C, we're going to calculate how much the investment would be worth after 10 years of quarterly compounding. Okay, so starting with the same principal, we still have $500. And now we're thinking, all right, well, if it was, compounded quarterly, we said it would be like 1%, so that's 0.01. But for 10 years and 4 times. Okay, so that's where this 4 is coming from, because if I'm doing it quarterly, I have 4 times a year that I will be compounding this. But keep in mind what we found back here. If I'm compounding it quarterly, it's only 1% per quarter. Okay, so if we were to multiply this out, plug this in, our total investment would then turn out to be about $744.43. Notice the difference from our first answer. Nothing huge, but if you had either a bigger percent or you did this over a longer period of time, you would actually earn more money if it was compounded 4 times a year rather than compounding it only once. Okay, so the pattern is fairly straightforward. For shorter compounding period, we get to apply the interest more often, but at a lower rate. So with that in mind, let's see what this would look like. So it says, how much would a $1,000 invested at a nominal 2% yearly rate, compounded monthly, so we have to think monthly now, that's going to be 12 times. Okay, and we're going to see how much that's going to be worth in 20 years. So again, that $1,000, that's going to be our principal. Okay, so that is what we are investing. And we are going to be doing this at a 2% yearly rate, but compounded monthly. All right, so I want to add on to this 2% as a decimal, but I'm not doing the full 2% because we're compounding it monthly. So I need to divide that into 12. That would give me the rate that I would be using. Now keep in mind what's going to happen up here. Well, I need to do this for 20 years, but 12 times a year. Okay, so plug that into your calculator. And our final calculation, we're going to get about $1,491 and about 33 cents once we round. And that would be how much you would have after 20 years at 2% compounded monthly. So putting this all together, I'm hoping we're coming up with a pattern that we're seeing. And this is going to give us our final formula. So it says for an investment with the following parameters, we're going to write a formula in for the amount the investment is worth, which is our A, after T years. So this here, the amount that your investment is worth. Okay? P is the amount initially invested. We call this the principal. R is your nominal yearly rate. And N is the number of compounds per year. So think about that. Okay. So we said we start with your principal. We have 1 plus. We took your rate, but don't forget we had our number of compounds that we had to deal with. So we took our rate divided by the number of compounds. And then we took it and we had our exponent up here. We had our number of years times the number of compounds. So the number of years times the number of compounds. That's your formula. If you can remember that formula, you got this stuff made. Okay. We're going to try this. So, exercise 1, it said referred to as a nominal in name only. That's what that means. It's known as this because effectively you earn more than this rate if the compounding period is more than once per year, which we saw. It was a little bit more, nothing huge. Because of this, bankers refer to this as the effective rate, or the rate you would receive if compounded just once per year. So, an investment with a nominal rate of 5% is compounded at different frequencies. We're going to give the effective yearly rate, accurate to 2 decimal places, for each of the following compounding frequencies. So we have a 5% rate, and we're going to compound it quarterly. So think about, this is that parenthesis part of that formula. So we have that 1 plus and our rate. Our rate, 5%, would be 0.05 as a decimal. And if we're compounding this quarterly, I need to divide that by 4. Now, don't forget, what do we have up here? So up here, we're going to have our years that we're compounding this and the number of times. Okay. We only want this for 1 year, and the number of times we're going to be compounding this is 4 times. Okay. So plugging this all in, I would get something, when we calculate this out, it looks like 1.05094. Okay, so now I have to think, what's the rate? Keep in mind, our formula always has this 1 in front. Your rate is going to be coming from this decimal part. And again, I want to think now, if I'm taking my decimal, putting it into a percentage, move it 2 places to the right. So that would give me about 5.09%. Okay, so a nominal rate of 5%, but compounded quarterly actually turns out to be about 5.09. Doing the same thing monthly. Okay, so what's going to change? Well, your rate doesn't change. Rate's still 5%. It's the compounding frequency, which that's going to be 12 since we're doing it monthly. Okay, so now again, up here, I'm going to have the number of compounds times the number of years of that investment, which again, yearly rate is only 1. Okay, so plugging this in, I'm going to have 1.05116. So again, if I want the rate, just looking at the numbers after the decimal place, moving that 2 places to the right, I'm going to have 5.12 with rounding percent. Notice we're actually getting a little bit more if we compound it monthly. Okay, so daily, how does that change? Well, your compound is now going to be 365 for our frequency. Up here, 365, and again, the number of times for the year is just 1 year. So multiplying this out, we're going to get about 1.05126. And again, if we look at our rate, that's going to give us about a 5.13%. So again, the number of frequencies, as that increases, so we went from 4 to 12 to 365, you're going to see that rate actually looks like it increases a little bit too. Okay, so we would compound at a smaller and smaller frequency intervals, eventually compounding all moments of time. In our formula from number 3, we would be letting the letter n approach infinity. So interestingly, this is going to give us a new formula, which is going to be called our compounding continuously formula, and it uses the natural base e in this compounding formula. Okay, so you're going to see this looks very similar, but notice what has been replaced. That e replaces our formula that we had, that 1 plus r over n. So that's what they're saying there. So as n is approaching infinity, as n is getting bigger and bigger and bigger, this number actually looks like it's approaching that number e that we've learned about. Okay, so that gives us one more formula. So a person invests $350 in a bank account and promises a nominal rate of 2% compounded continuously. So we're going to write an equation for the amount of this investment would be after t years. So we're going to use this compounding continuously formula. So we have our amount. We still have our principal, so we have 350. Now we have our letter E, and we're going to raise it to the rate times time. And since our rate is 2%, we express that as a decimal. And our time we don't know right now, we're just saying t years. So that's our basic formula. Okay, so now for letter B, how much would the investment be worth after 20 years? So in this formula, now I have a value for t. I know that that's got to be 20. So we have 350 e raised to the 0.02 times 20. So plugging that in, we're going to be rounding, simplifying this out, we're going to have about $522.14. Okay, so now it asks us to algebraically determine the time it will take for the investment to reach $400. So I know this 400, this is this value up here, the A of t. Okay, so I could say $400, that's what it is. I know my initial investment is $350, compounding continuously at a rate of 2%, and I'm trying to figure out the time. Okay, so very first thing that we would need to do is, in order to solve, we need to divide each side through by 350. So on the right side, we're left with e to the 0.02t. And on the left side, we get about 1.14286. Now, in order to solve this, I need to get rid of the e. I have to do the inverse of e. The inverse of e, remember, is your natural log. So what you do to one side, we need to do to the other. And since those are inverses, they would reduce out. On the right-hand side, I have 0.02t. And on the left-hand side, I have the natural log of 1.14286. So in order to solve for t, I'm going to divide through by 0.02. And we're going to see our time nearest tenth of a year is going to give us about 6.7 years for our nearest tenth. Okay. Then it says, what is the effective annual rate for this investment? So think about how we did the annual rate before. It was just that middle part, that parenthesis part. Well, that parenthesis part is now that e part of the formula. So we have e raised to our rate times 1 year. And if we plug this in our calculator, we get 1.0202. Remember, the rate is coming from this decimal portion. turn that into a percentage, I'm going to have 2.02%. So again, notice how that's a little bit more than that actual 2% rate. Okay, bring any questions you have to class, and we will discuss. Have a great day.